Okay, so in this example, we're going to talk about pushing contours. Pushing contours are one of the skills you're going to need in order to create conceptual drainage plans. The great advantage of pushing contours is that it allows you to very quickly try out a couple of ideas. And I'm sure this looks familiar to you. You've seen it last semester. This is a simple case of a slab, a building on a sloped site. And I know if I asked you what's going to have to get the water around the building, we'll play that game to start with. You know, I've got water running down this hill here. We all agreed on that? And as it is, water is going to run straight into that building. How am I going to stop that from happening? So you're going to have a swale going around. You guys all know this. So that being the case, you also know that when you put a swale in, it will often look something like this. How many of you would be able to draw that just off the top of your head, say, yeah, that's what a swale looks like? And you would come down and connect this here if you wished. And if you're lucky, and look, I was lucky, I happened to pick the same contour on both sides. That wasn't on purpose, but I got lucky. And then you already know that you could do this. If the coffee cup was not in the way, I'll move the coffee cup to the other side of the computer. And then you could do this. And then this. So this is just pushing contours, folks. This is all it is. Think of it like wet spaghetti. And you have the ability to do this now. You know how to do this. You also know that I ran out of room here. And you also know that these contours here might be too close. But this is a basic swale pattern. And you know that this one could come up and back like that. This one could come over and this one could come over. You have that ability right now. You know how to do this based upon your knowledge from last semester. You might be asking, well, why didn't you just show us how to do this to begin with? And why'd you make us go through all that math and learning how to do this mathematically? And the reason is, frankly, without the math, you wouldn't know that these puppies are too tight. And without the math, you wouldn't know that you need to go and check the distance here to see what that swale slope is. But because you've done this before, you know that that swale has to have those contours spaced out as much as it can to keep things from running too fast. Because otherwise, if you hadn't had that knowledge, you might do something where you say, all right, you know, we're going to, you know, go, I don't know, we'll pick this one up like this, back, around like this, and then your next one might be up like that, and really tight, and then down, and you might have made them really close to one another, maybe even they touched, or you might have said, well, this one's just going to come down like that and then go up here, and then the question is, would water actually be able to drain? So there are reasons that we didn't show you pushing contours right up front. And frankly, the reason is you didn't have the knowledge. The other thing is that you notice I went around the building, but of course, in this case, you know, you can just come and hit the building. And now that we're allowed to just touch the building slightly, this thing gets a bit easier. And it's a lot less impact on the site. Did I connect that to the right one? Nope. Sorry. Let's go back. 84 to 85. That's right. So this one could just come down like this to 84, and then it could just connect right back there to the 84. This 83 could just come around, hit 82, 81. Now, of course, you still have the problem that water's coming down this direction, so you might want to actually bring this one further up in. So I'm showing you this so that you can understand that pushing contours is a skill that you should have by now. And you know then that you could take, all right, let's try it with this contour and see what happens. That means that this one goes up, over and connects here. This one goes over, connects here. This one goes over. And these are really simple down below. So we get different design solutions based upon where we decide the elevation for that high point should be. Do we go with 84.5? In other words, 84 goes below. And you can tell that just with these three little sketches, pushing contours allows us to test out ideas. The ability to test out ideas quickly is what is going to make you a good designer, because you will be able to grade your designs. So frankly, I would suggest that each of you take this little drawing and try that out this week. Because if you cannot push contours around this little slab, you're going to be struggling almighty as we try to grade this much larger project. And I need you to develop some confidence with pushing contours. I know some of you developed this confidence last semester, but I need all of you to develop this confidence that you can push contours and that you know that you are reasonable because you understand how far apart the contours need to be reasonable, because you've looked at the slope triangles. You might notice that when I was pushing contours, I didn't do any math. I got 3 different concepts with no math. That is valuable. So here we have another example. Should again look familiar to you. And we can do the same sort of thing with this. You guys can push contours on this. And to begin with, you know that, okay, I've got water coming down from this side up here. And so I'm going to need to have some sort of a swale that, you know, gets that water off to either side. Nothing new there for you. Luckily, you've seen this idea before. So you actually can, because you've done this sort of stuff, start pushing contours right now. You could say to yourself, okay, well, what if the 65 went up and then came back down and around, and then it went up and back like that? That would make the top side very easy, wouldn't it? So up here, no problem. You know, we know what we're doing there. The difficulty is now we've got to start stacking all these contours down here. You know, you got to take the 64 down, the 63, the 62, the 61, and you're not sure that you want to, but we can try it. So let's take that 65 up, around, down, up, back, over. Can we now get the 64 down, across, over here, up, 63 down, across, over here, up, 62, it's getting tight, folks, it's getting tight. And then your question becomes to yourself, okay, self, that's lovely, but how far apart are these contours? Does that make sense? How far apart are those contours after I push them? And I'm looking at this and I'm thinking, well, on average, they're about 10 feet apart. 10 feet apart is how much slope? 10%, yes. Is 10% an acceptable slope for a driveway? You guys know that you could possibly go with, 2% up here at the top, and then maybe 8% down here at the bottom. But you also know that, maybe we shouldn't be pushing that 65. Maybe we should be pushing, instead of pushing the 65 up around, maybe it should be the 64 or maybe even the 63. Now, last semester, that would have been a huge amount of work for you because you got to redo the whole thing. But we are going to say, no, we are simply going to let's try the 63 at the other end. So if we take the 63 up and back down and around, Ran into the coffee cup again. Whoa, that's a long ways down. Now we know we have challenges with the 64 getting a little tight there, don't you think? 64 coming down. This is interesting doing it with a mouse. I guess I could do it with my pen. Wow, that's a squeaker. And then this one coming down. But on the other side, now all we have to do is get the 62 across and take the 61 across. So contours that are 20 feet apart, what kind of slope is that? 5%, yes. Is 5% a better solution for a parking lot or for a driveway than 10%? Yes, it's clearly a better solution. The other thing is we can look at that and say, oh, well, you know what we could do? We could take this 62 and pull it down even further and back up, and then pull the 61 down further and up. So now we have a relatively flat area here and a much steeper area down here. Now, did we do any math to do this other than what we had in our head? And here's the question: how did we find 5%? Contours that are 20 feet apart are a 5% slope. And how do we know that? We go back to our slope triangles and we take a look at those, and we will see that contours that are 50 feet apart, that's going to be 2%. So you need to start to become more comfortable with those triangles that tell you, how far apart contours are with the slopes. And I can bring that back up in a minute, but it is available to you still from last semester. And I think we have it in our resources here, that little graphic I put together of slope triangles. For your concepts, you can grade everything with 2%, 5%, and 10%. I'm going to repeat that. For your concepts, you can grade everything with 2%, 5%, 10%. I also want to show you that this swale right here, how many of you think that swale might have a problem draining? And that means that it doesn't have enough slope. So we know then, just looking at that swale, that this contour is going to come back up inside of that swale and then come down for us to get enough slope on that swale to drain. So again, this is one of the reasons we didn't just teach you pushing contours first, because it'd be very easy to overlook that swale is not steep enough until we pull that contour back up in there. Again, you're not really going to that level of detail for what you're doing for Thursday or for next week. But the knowledge that I can say to myself, okay, self, what's the distance here to here? And now I can look at that and I can look at the scale and say, oh, that's maybe 25 feet. And at 25 feet, you know that has enough slope that it will drain. We could actually go to 50 feet and it would drain, but I would rather not stretch it that far. So this is the idea of just pushing contours, which you guys need to get comfortable with. And if you're doing a parking lot, so we're going to take that exact same plan and we're going to throw a parking lot on it. You want to start by saying to yourself, all right, I've got a couple of ways I could drain this thing. Just looking back at the set of drawings that we had up a minute ago, these guys, I could throw any of these patterns on that parking lot, but I should probably pick one that, you know, fits the land well. And so, okay, we'll look at number 9 here. Then we're going to go back over and look at this. It's like, okay, well, we kind of have water running, you know, at an angle, and we do have diagonals running. So we could start by saying, all right, let's just put in a line across the parking lot here. And then let's put in another line that is 50 feet away. Okay, and my guesstimate on 50, looking right here, I'm going to say that's about 50 feet. So I'm going to put a line in here at 50 feet away. Then I'm going to put another line down here at 50 feet away. Now this is an estimate, and of course you can measure. I have no idea if this is to correct scale, but that is good enough for right now, because I know that this is 50 feet here, and I can run these measurements. You know, I can measure that if I wish, and then I can put these in at 50 feet. If that is 50 feet apart, what is the slope if those are 50 feet apart? That is a 2% slope. That is correct. Now, do I have to use the 2% slope? Nope, I don't. I could come back in and say, you know, I'm going to make those guys a little closer. And just because I want to. So I'm going to make them 40 feet apart. So here's my first one. And I've got an exact measurement over here for 40 feet. So here's my next one again at 40. And here's another one at 40. And maybe here's another one at 40. Now, I'm not perfectly drawing those in. The closer we can get to 2%, the better. But anything between 2 and 5 is acceptable. So now I've got these puppies drawn in, and the question becomes, all right, Stuart, does that even work? Can I take this one and connect it to there? Can I take this one and connect it up to there? This one to there? This one's like, oh, dear, 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 dear. That's getting a little more difficult. By golly, we just graded a parking lot. Does that seem ridiculously easy? Almost deceptively easy? Like, all right, what's the catch, Stuart? So let's do it again. Let's come in, and I like my slope to mimic the natural site that's there as much as possible. And I don't like that last one. Pull it down a little bit. So, you know, that's about 40 feet apart. Can we agree on that? And if that's the case, could this be any easier to grade now? So what you want to do is you want to try to replicate what you have on site as much as you can when you're doing your parking lot design. Now, I was not taught this in school. And when I discovered it, it kind of blew my mind. It's like, well, why did they make all this stuff so darn difficult? Because it doesn't need to be that difficult. We'll do it again. Let's see if we can get it any closer. We're going to start down here on this end, and we're going to say, all right, here's my first one. There's my next one. There's my next one, and this one will be about there. I don't like that one. It's not quite spaced as well. And this one can connect to there. This one can connect to there. This one can connect to here. This one can connect to there. And I can even move this one down a little bit. And my grading's done. Do you follow this concept? Because this is a critical concept. We need to know the distance between these. We need to make them a consistent distance. And that is how we're going to grade our surfaces. We're going to try to line it up as best as we can with the naturally existing contours on the site. I will tell you that this example is extraordinarily easy. Your big site plan will be a little more challenging. But how do you stop water from the top? Well, let's go back and see. That we might have, this might turn around and create a swale to run water that direction. And that would then run water off. So that is how we might do that. So I have lots of ways, lots of choices we can make here. So for example, I could say, all right, I'm going to have my lines, I'm going to try that V pattern. Then I might come in and say, all right, and then I might connect this up here, and I might connect that one up there. But frankly, one of the things you're going to discover is that this V pattern might not work so well for this site, because the existing contours are running, whoa, that was poorly done. The existing contours are running this direction. So if the existing contours are running this direction, we want to try to keep with those existing contours. If the existing contours were in a different direction, then we would do something different. What about the tilted V? Do something like this. So there's a V. I'm going to move that last one down just a little bit if I can. And now I've got to connect those puppies in. That one would seem simple, except we still have water draining down. So we're not too worried about that yet. But we're going to come back to that top one. We're going to stick to these down here for now. Wow, that couldn't be easier. And it looks like our driveway is going to get a little steeper. Now, you notice I left this one at the top, and I left it because we might need a swale in there with a high point to get water off to the sides. So the fact that we have a V going across this is perfectly fine. Having a V going across it, in this case it's a ridge line, is absolutely fine. You do not have to keep all of these contours in the same pattern. You do need to keep the space in the same, but you do not have to keep them all in the same pattern. You will definitely have V's in your design on your project because your site naturally has a ridge line running down the middle of your parking lot. I'm going to say that again. You will have V's in your design because you have a naturally existing ridge line running down your parking lot. Questions on this before we move to the next one? Or would you guys like a break?